Today we're going to talk about the different geological and hydrogeological provinces of the United States. Um, this is hydrogeology from sort of 30,000 feet, and it's really mostly relevant to things like water resources. So where's the water being stored, and how significant are the water, or how significant are the aquifers that are there? So a couple of things to know before we get started. One is that in general, as you go deeper underground, and this is not just maybe hundreds of feet, but in some cases thousands of feet, in general, the salinity of the water is more likely to be high. More likely to be high. So a lot of the fresh water, the really potable, clean water, is up near the surface, and that's because it's more likely to have been recharged recently by rainfall. The water that's deeper in depth is more likely to have been there for a long time, and it's often more likely to be present under slightly higher temperatures. One thing that geologists and hydrogeologists consider in terms of water chemistry is the something called the water-rock interaction. So the more time that water has to interact with rocks, the more time it has to possibly react with those rocks, to dissolve them, to break them down, and therefore for the constituents of the rocks to begin to be added to the solutions. So things like a very common mineral like a feldspar, which is the big pink things that you see in granite, has the formula KAlSi3O8. That's a potassium feldspar. Well, potassium is pretty soluble in water, and so you often see a lot of potassium floating around in water. You also see, whenever you are in domains that have a lot of calcium carbonate, the calcium gets added to the solution as the calcium carbonate breaks down and so forth. If you had salt deposits, salt is sodium chloride, NaCl. Salt, as you know, is very soluble. It dissolves right away in water, and so you'd have sodium and chloride in there. And then this CO3 molecule that is often associated with calcium carbonate is called a carbonate molecule. And when carbon dioxide dissolves in water, or when limestones dissolve in water, that carbonate molecule becomes what's called bicarbonate, or a lot of the carbonate molecule becomes bicarbonate. And that's a very common constituent in water. So you can actually, if you were to just look at the chemical composition of water, like bottled water or something, you should be able to tell a lot about what kind of aquifer, not what kind of aquifer, but what kind of rock the aquifer was made of that held the water that was then bottled. So if you have a lot of bicarbonate, you're probably in a sort of a limestone terrain. If you have a lot of dissolved silica, then maybe you're in a more granitic terrain, like someplace like in the Rocky Mountains, or maybe in the Northeast in Vermont, or in upstate New York or Maine, or someplace like that. Okay, so that's that. So what we're going to do is we're going to kind of talk about generically what we think about in terms of the potential for aquifers around the country, or in different geological provinces. And then we'll take a break, and when we come back, we'll sort of go through area or region by region across the United States and look at sort of where the aquifers are located. So some of the big aquifers, some of the best aquifers in the world can be located in any geological province. It doesn't matter if it's a lava flow or a mountain, or a place like Florida, which is very flat and low-lying, or whatever. The areas that often make some of the best aquifers are alluvial aquifers. So we have something that looks like this. So this is This is the floodplain of some river. This is the river itself right there. And remember we talked about how rivers are very dynamic systems, so that when you look at them, this is obviously a cross section. When you look at them from space, say in terms of topographic lines, you'd have, the river. This is now north. We're looking at it from space. This is the river sort of snaking its way from the top to the bottom. It's very flat in here, so there are no topographic lines over here. This is like, who knows? This is a hillside going up. So this is the floodplain. From here to here, right? And then these are topographic lines. So this would be like 900 feet, 910 feet, 920, 930, 900 feet, 910 feet. So it's rising up on either side. Well, remember, the rivers are constantly migrating around, and they're constantly both eroding in the cut banks and depositing in the point bars sediment. And that sediment is constantly being reworked and deposited and transmitted downstream. Well, if you were to look at that, take a vertical slice through a floodplain, what you'd see is just tons and tons of the sediment, sometimes little gravelly layers, sometimes sandy layers, sometimes silty layers, right? Whatever the stream happened to have left behind, that are being deposited not only in the point bars, but also whenever the river floods and spreads water and sediment out across the top. So these are unconsolidated sediments, meaning they have not yet been cemented together into solid rock. You could take a shovel and you could start digging down through these things. And these can be very, very deep. I mean, they can be hundreds, they can even be thousands of feet deep, although that's a little bit of an exception, but many hundreds of feet deep generally. And they can be very, very broad. And then the porosity is quite high. So, and of course, you've got a source of water right there in the river that is interacting with the aquifer. Now, when we talk about streams or rivers and aquifers, we often refer to two types of streams. So the interaction of streams and aquifers can be thought of basically in two scenarios. One is where the stream, which is here, it's a tree, intersects the water table, and the water table looks like this. In this case, because this is the water table. In case the hydraulic head is higher than the stream, the water is flowing and discharging out of the ground into the stream like this. So the stream is actually gaining water from the ground, and as a result, it's called a gaining stream. This is what you get in most relatively low-lying areas, humid areas, as we have in Iowa. So if it stops raining, and it doesn't rain for a long time, the water level goes down in the stream, but it goes down very, 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 very slowly because there's still water from the ground that's seeping in, keeping the stream flowing. And it takes a long time for the water table to drop to the point that it's below the stream, at which point the stream will finally go dry. But that takes a really long time. In more arid environments, you get something that looks like this. Where there's the water table. So in this case, the water is seeping out of the stream and raising the height of the water table. The reason the stream is flowing is not because it's raining anywhere near here, but because it's maybe raining or snow is falling and melting up in the mountains, maybe dozens or hundreds of miles away. So the water is being lost from the stream to the underlying aquifer. So you get a bulge in the height of the water table below the stream. But as soon as the water, meltwater, is no longer supplied to the stream dries up, right? And what will happen, of course, is that the height of the water table will begin to fall. This is called a losing stream because the stream is being lost, or excuse me, the water is being lost from the stream to the water table. So if this were to, if this losing stream were to suddenly go dry, then what would happen is that the water table, which looks like this, would very quickly, water would be flowing out like this from where the hydraulic head is the highest to where the hydraulic head is the lowest, and over time it would flatten, right? After some amount of time it would look maybe more like this, and then a little bit later it would look, something like this, and eventually it's going to reach the point where it's flat, at which point the water will stop flowing, right? It'll just sit there. Okay, but that would take a long time. All right, so in terms of geologic resources, alluvial aquifers are great. And you can find them anywhere. Anywhere that there's a stream channel or an ancient stream channel, you can get alluvial aquifers. And some of you guys, I believe, were looking at, in your research papers, you're looking at these alluvial aquifers. In some cases, they're ancient. They're formed even from rivers that have long since stopped flowing, and they've deposited these big sedimentary package. You can also get alluvial fans. Alluvial fans aren't formed in riverbeds, but they're formed on the sides of mountains. So you get a mountain like this. Here's a tree. And of course, over time, the sediment is eroding and tumbling down the side. And so you get these big, thick sequences of sediment here. And it's gravel generally. It's generally pretty coarse grained stuff. Gravels and cobbles and sands that are sort of formed by erosion. These are eroded from the mountain and deposited on its flanks. And they, depending on their size, can make for very good aquifers. They have a lot of high porosity again. The problem with the alluvial fans is that they're often kind of narrow and small, but sometimes along big, long mountain range fronts. So here's a mountain, all these different mountains. This would be a scale of, maybe hundreds of miles. You have all these separate alluvial fans. So here's the top of the mountain. That's a snow-capped mountain, right? And the sediment is kind of washing off each one, forming these little triangular shaped fans, but the fans all kind of grow together. So each one of these is an alluvial fan. Each one of these is a mountain. And so this is all the sediment that's sort of come washing down and piled up on the flank of the mountain. And so they coalesce together into this big sort of an apron that rests on the front of the mountain front. And as a result, you can have these very extensive alluvial fan aquifers. Intermontane basins are a geologically really good place for an aquifer as well. So if you start out with a series of rock layers that looks like this, and you put a crack or a fault through the rock that looks like this, and you begin to slide this side down and this side up, right? Over time, what you're going to end up with is something that looks like this. Here's our tree. Okay? So this side, the right side of the fault, used to be continuous up here, but it slid down. And in many cases, this happens in little jumps and starts, with earthquakes happening every couple of years, or a couple of dozen years, or a couple of 100 years, but it goes on for a really, really, really long time. And as that's happening, you are beginning to weather the rocks, erode the rocks along this fault scarp, it's called, this sort of plane that the rocks have been sliding down along. And so the sediments begin to erode off of here. They erode from here, right, and form these sort of alluvial fans. But the faulting continues, so that over time, the offset along some of these faults can literally be in the span of 1 to 2 miles. And so when you're sitting on a, let me do this again, when you're sitting in some places like in the Rocky Mountains out west, or other areas, the Great Basin, you have these kind of layers of rock that go down like this, and then you've got some other area here, and then who knows, maybe it goes on again, right? And all of this is sediment. This is all loose sediment that's been shed off these mountains over time. And again, this depth can be thousands of feet. And this thing here is a mountain. So when you're standing at the base of a mountain looking up, it's sometimes pretty fascinating to think that sometimes a greater distance than the height of the mountain exists below your feet in these big packages of sediment. In some cases, it'll actually, you have a mountain, and you'll have one of these things, and then you'll have, I don't know, something that looks kind of like that. So you have another mountain. And this is all this intermontane or between mountain sediment. These things are called basins, sedimentary basins. And these sedimentary basins, again, can be massive. So the city of Albuquerque sits right there. Salt Lake City sits on something kind of like that. Anyway, so lots of places out west exist. Okay, where else do we get good aquifers? We can have aquifers obviously in any kind of rock. The rocks that, when you look at them, have these crystals that you see, like a granite. If you ever look at a granite countertop, there'll be this interlocking network of crystals, and some of them are kind of square, and some of them are a little bit round or whatever. But we refer to those as crystalline rocks, and these are rocks that are formed through the cooling of a magma, which makes it igneous, or through some sort of metamorphism. And as a result, they generally have very low porosity. But if you want to increase the porosity, what do? You fracture it. So fractures and faults are the primary, fractures and faults are the primary location of water storage in crystalline rock aquifers. The amount of porosity between these interlocking crystals is really low, but they're also very kind of rigid, and they're often found in places where there are or were mountain ranges, and so they get cracked and faulted and fractured. And as a result, there's lots of space for the water to be held in. In other areas that are limestone dominated, the thing that's special about limestone is that it's quite soluble. Remember, it's calcite, it's calcium carbonate, and this stuff is quite soluble, so you get dissolution that can create big openings like caves. The generic term is karst, K-A-R-S-T, which means that the limestones have been dissolved. And that allows, of course, you take a small fracture and you dissolve it into a bigger fracture, and suddenly water is pumping through there like crazy. So limestone aquifers exist all over the United States and all over the world, and they're just fantastic aquifers. One way that you can look for areas of limestone, of course, is you just look for caves. If you just look at a map of the United States with caves, you will know what areas have lots of limestone, and therefore what areas are going to have good aquifers. What else? I think that's probably it for now. So we'll come back and we're going to talk about, look at different geologic and hydrogeologic regions of the U.S.